In the previous lecture, we looked at topological dynamical systems, and in particular at the shift map and the subshifts. So this is considered a topological dynamical system because all you are considering is the transformation of a topological space under continuous mapping. And then you're interested in how this behaves topologically. So where are the open sets going and so on. So where are cylinders mapped and so on. Now we want to enrich this by a measure. So we're, in addition to the shift map, the pure shift map, we're also looking at, we're putting a measure on our space and look how the space then behaves measure-theoretically under the shift map. So this is called measurable dynamics, because you're now interested in questions like where do the majority of the points go under this mapping. Right? So that is measure, where does the most of the measure, how does most of the measure behave under the transformation? We start with a brief review of stochastic processes. So as usual, let A be a finite alphabet, and let xn be an A-valued process. Recall that the joint distribution of the process is given as a sequence of probabilities Pn, where Pn records the distribution of the process up to time n, namely it records the probabilities that x0 is takes value a0 and up to xn takes value an, where of course these here run through all possible combinations of values from a, and we write short p sub n just a not up to an for this. And these joint distributions are subject to the consistency requirement that Pn of a0 up to an is the sum of all Pn plus 1 of a0 up to an, comma a, where a runs over all entries, elements of the alphabet. So, and we saw then that the Kolmogorov extension theorem lets us construct an underlying measure. So for these random variable here have a common underlying measure space, and this measure space can be constructed via this extension theorem on the sequence space a to the n, and then it represents the process in the sense that mu, so the measure of the cylinder given by sigma, is just p sub length of sigma, right? So, and we saw that this is kind of the key to it, this consistency requirement. This is corresponded to the consistency requirement we had for measures defined on sequence spaces. So the Kolmogorov extension theorem is the bridge that lets us get from measures on the sequence space to stochastic processes and vice versa. An important class of processes are the so-called stationary processes. And those are processes where the joint distributions will not depend on the choice of time origin. That means it does not really matter if I start the process at time 0 or if I start it at time n. So that means I put the origin then at time n and start the process from there. Formally, stationarity can be described as follows. We just have to require that the probability, right, that xi is equal to ai for I between m and n, so for a time interval between m and n, is just the probability, if I shift this time interval now by 1 here, and xi plus 1 is equal to ai, right? But the length of the interval is the same. And of course then that inductively lets us shift the time interval by any amount over time, right? Probably the easiest example of a stationary process is just the uniformly distributed process. So let's assume that A is just the binary alphabet, and just set P of xi equals 0, right, is equal to P of xi equals 1 is 1/2, and that's for all I. And now it's easy to see that this is a stationary process. So let's let this be here x0, and x0 can take values 0 or 1 with probability 1/2, and then this can take x1 can take values 0 and 1 with probability 1/2. And this continues now for x2, x3, and so on. But it's easy to verify now that, for instance, the probability that I see 2 consecutive zeros at the beginning of time is the same as the probability that I see 2 consecutive zeros at a point later in time. Let's see at time 3. More generally, we obtain a stationary process whenever we have an IID process, so independent identically distributed. We saw in the homework that in the case that A is the binary alphabet, this is the case that we have our distribution P of 0 is P, and P of 1 is 1 minus P. Right, in this case, we also obtain a stationary process. The Kolmogorov extension theorem now lets us pass from a stationary process to a measure with a property that is invariant under the shift transformation. So if we have xn, a stationary process, then we let a to the n be are the Borel sets on a to the n, and mu be the Kolmogorov extension or representation to the sequence space. Then it holds that this measure mu is what is called shift invariant. What does that mean? Well, first of all, note that if T is the shift map on a to the n, well, we encounter that in the case of the subshifts. Well, how does the shift map behave on cylinder sets? So let's look at a cylinder A0 up to an minus 1 that starts at k. Remember, this notation just means that this is the set of all sequences x, so set of all sequences x, such that xk is a0 and x sub k plus n minus 1 is equal to an minus 1. So if we shift this back, or shift this by back by one position, right? We take the pre-image, well, then we just get the cylinder with the same values, only that those values now start at position k plus 1, right? So the pre-image of a cylinder under the shift map is a cylinder of this form, right? These generalized cylinders. But this means that the pre-image of a cylinder is a Borel set, because this is clearly a Borel set. Hence, the pre-image of a cylinder is measurable. And this property now carries over to the whole family of Borel sets, namely meaning that the pre-image of a Borel set under the shift is still Borel for any Borel set in the sequence space. And that is precisely the definition for a mapping to be measurable. So the shift map is measurable. Furthermore, since our process is stationary, what does it mean for the Kolmogorov measure? Well, the measure of the cylinder of a naught up to a n minus 1 at k is the same as the measure of the cylinder starting at k plus 1, right? That's just stationarity, right? This time independence. But we saw here, this here is the pre-image of this cylinder, so the previous cylinder, under the shift map. And this property here, again, right, mu measure is the same as the pre-image of this set, extends to all Borel sets, right, using the definition, the way that Borel sets are defined, by closing the open sets under unions and complements. Well, and this means that we have the property that for all Borel sets in the shift, that the measure of the pre-image of the Borel set under the shift map is the measure of the set. So it does not change. And we then say that mu is a shift-invariant measure, or if we want to talk about the transformation, how it behaves with respect to measure, we say that T is a mu-preserving transformation. So together with the shift map T, this Kolmogorov measure space, a to the n, Borel sets, and the Kolmogorov measure mu, corresponding to this stationary process xn, forms what we call a measure-preserving dynamical system. So a measure-preserving dynamical system, in general, is a tuple x, a mu t, where this is a probability space. A is the sigma algebra of the space, right? X is the set and mu is the measure. And T is a transformation that maps the space X to itself, and that is measurable. That means the pre-image of any set in the sigma algebra is in the sigma algebra, and is measure-preserving. Which means now, just as before on the previous slide, that the measure of the pre-image of any Borel set is the same as the measure of just the Borel set. So if you want to illustrate this, you can think of this as our space X, and now in this space we have a Borel set B, right? And now we take the pre-image of B under T, so that might split up B, something like this. So these are the two halves, and they both together give us the set B. So this is T minus 1B and T minus 1B here. But the important thing is now that the measure of these things, so think of it, the area here of these things, of these sets, remains the same. So there's no change in measure of these sets. So measure of this measure is equal to mu of B. An important example of such measure-preserving transformations are the Bernoulli shifts. And the easiest way to obtain a Bernoulli shift is just taking the Kolmogorov extension of an IID process. So let A be, for instance, be the binary alphabet, and P be a value between 0 and 1. And then the measure mu P, that was on the homework, right, of an IID process, the Kolmogorov measure of this is just given by p to the n times 1 minus p over length of sigma minus n, where n is just the number of ones, so the number of occurrences of ones in sigma. And that indeed is a shift-invariant measure, right? That just follows from the previous slides where we looked at IID processes, right? And then the system of the sequence space Kolmogorov measure plus the shift is the most simple example of a Bernoulli shift. So once again, the Bernoulli shift looks like this. Then we start and split by p and 1 minus p between 1 and 0, and then we continue this 1, 0. So here we have p squared, here we have p times 1 minus p, and so on. And here we have 1, 0, and here we have 1 minus p squared, and so on. And again, it's not hard to see that this is indeed a shift-invariant measure on the sequence space. One often also looks at the two-sided Bernoulli shift. So the only difference there is that instead of looking at the sequence space a to the n, we look at the bi-infinite sequences, a to the z, and the measure can be defined in the same way. We can extend it in a straightforward way to cylinders on the two-sided shift. Right? And looking at the two-sided Bernoulli shift has the advantage that, as we saw in the previous lecture on subshifts, that the two-sided shift is actually invertible. So this was a rather simple example of a Bernoulli shift. The general concept of a Bernoulli shift is that we start with any just probability space x a mu, and then we just take the product of this probability space, and here we look at the two-sided product. So we go from minus infinity to infinity, right? And of the where each component of this product is our original space, right? And we take the product sigma algebra, the product measure, and so on, the product space here of the x's. And then this space here is invariant under the shift t from y to y, where t of y now, so an element of y is now a bi-infinite series of entries from x, right? And now we just shift this, where we just say the nth entry of this image of t of y is just the n plus first entry of the original series. So this is called the two-sided Bernoulli shift with the state space x a mu. Okay. This should make it clear that Bernoulli shifts can be a very, very general concept, right? So because we can start with any probability space here. We finish this lecture by noticing that we can actually go back from shifts to processes, right? So if we start with the shift-invariant measure on a sequence space a to the n, then we can derive a stationary process from it in the following way. So first, we partition a to the n into these parts here. P sub a is just the set of all x's that have a in the 0 position. Right? That's P sub a. And of course, in our notation, that's just the same as the cylinder given by the entry a. That is the set of all sequences that have a in their first position, right? Which is precisely this set. I gave this notation here because it's often found in the literature. In fact, this partition here is called the Kolmogorov partition. And behind this is a very general concept. So if you just don't think of a sequence space right now, it's just we we start by partitioning our underlying space, right, on which we have the shift-invariant measure, into a number of starting partitions. So think of these here as the set as the PAs. Now we can define an A-valued random variable by just mapping the element of our space, right, on which we have the shift-invariant measure, to A, right, where A is such that X is in PA, right. So think of our X here as the random element with the property that it has A in the first position. This gives us the distribution now at time 0. So this is the distribution of the process at time 0. And to obtain the distribution of the process at time n, well, what do? We just look where was X n steps ago, right? So this means that the distribution of the nth variable is just given by the distribution at the origin xp of tnx, right? What does that mean? Well, we shift x by n times and then look at the distribution of this. In other words, for xn, all those points get mapped to A, right, whose nth iteration ends up being in PA. Right, so if we have a point here whose nth iteration, Tn of y, ends up in being in PA, then this y gets mapped to A. In other words, what we're looking at here is the pre-image of PA under n iterations of T. So we're looking at T minus n of PA. Right? So this here, this area will, after n steps, be mapped to PA. And since T is measure preserving, this area has the same measure as our original PA. Yet another way of looking at this is to just pick a random point, right, in our space X, or A to the n in this case, and then let it wander according to our transformation T. So we look at Tx and Tx squared, T square x, and so on. And after each iteration, we record the member of the partition in which this iterated element point now lies. So the label A, and then maybe here we have B, so PB, and so on, right? And this way we get a sequence of an A-valued process, or realization of an A-valued process. And you can see from this is a very fairly general method, because we could do it for a process that is not necessarily, or a system that is not necessarily defined on a sequence space, but any metric space or measure space, and then just partition it in some way, and then obtain a process from it by just following points realization, right, a random element in the space, by following this point through the space and recording the element of the partition in which it lies. So this way we can actually turn every dynamical system into a system that is based on a sequence space, which is a very important method in the study of measure-theoretic dynamical systems. So that's all for this lecture. In the next lecture, we want to look at another example of measure-preserving systems, and that's Markov shifts. So those can be looked at topologically or measure-theoretically, similarly to the Bernoulli shifts, and they provide a very nice and important class of examples.